All right, good afternoon, everybody.
Good afternoon.
Your corals got sick this week like corals in a fish tank? Oh, wow. I bet that looks amazing, though. I tried a saltwater tank for about a year, and it was pretty cool while I had it, but I decided the secret ingredient to saltwater tanks is money, because it just kept getting more and more expensive. And then I felt bad because, like, I don't think I was doing a great job taking care of them, so I gave them to a graduate student who put the tank in his office, never did anything with it, and it was like beautiful after that. It just thrived and flourished, and so yeah, that's my only experience with coral. All right, so let's see. So, as someone mentioned in chat, make sure you turn in homework too, or have turned in homework too, or turn it in like right this second, because if it's 1 minute late, I'll give you credit for it. Um, Otherwise, it's a slip day.
I have a question
Go for it.
about branch instructions.
Okay.
Um, so I noticed in trying to do lab 2, and I'm not going to explain exactly how I did it, but I tried using a call instruction, which will come back to where I was at with return.
Mm-hmm.
But I found out that it would be easier to do it with a branch instruction, branch if not 0. The only problem is when I tried to use branch if not 0 and I hit the return at the end of my block of code, it would just restart the program and not go back to where I was. Is that supposed to happen?
Well, that's not what you wanted to have happen, but that is the correct behavior. Um, but we're going to talk about calls and returns either Thursday or next Tuesday. But basically, when you say branch or when you say go to, you're simply saying start executing code somewhere else. And there's no record of where you were before you branched or go to'd. So you're executing code, executing code, executing code. At this point, you say branch to some other spot. Now you start executing this code. And there's no record kept anywhere that you were here. When you do a call, however, if you come here, execute this, execute this, execute this, and then you say call this other set of code, you start executing this code, but the CPU remembers where you were when you said call. And then you can say return, and it'll go back to where you were when you said call. So call and return are what we used for writing functions, like in C when we say, here's a function and I want to execute it, and at the end of the function we say return. That's what these things do. Now, if you do a branch from here over to here, and you go ahead and you get to a return statement, the CPU says, I'm supposed to return to some location that I remembered, but I haven't remembered any location because I never executed a call. And so it doesn't know where to return to, and that creates an error condition called a stack underflow. And a stack underflow is not supposed to happen in normal circumstances. If this happens, it means something went wrong somewhere in the code, and the CPU throws its arms in the air and says, I'm just starting over. And it goes back and it begins executing your code from location 0. So that's why what you're seeing happening is happening. If you wanted to use a conditional branch, like branch if not 0, but be able to use a return, one way to do that, branch if not 0, some location stuff, and then at stuff, you could say call, whatever this thing is called. And then when you return, you'll come back to here, and then you can, continue branching or something like that. So there's no conditional call statement, but you could put a conditional statement, right before a call and make it conditional like that.
I wound up just doing a branch if not 0, and then it goes to a block of code, and at the end there's a go to the top of my main loop again.
Okay, that's good. That's the easiest way to do it at this point. And that brings up another thing that I wanted to talk about, which is this end statement. So every piece of code we see in a lab or in the textbook that represents a full program, there's always this magic word end as the last line of the program. And remember we talked about this is kind of a throwback to the days when, you know, maybe you had your program on punch cards and you'd put the stack of punch cards in a reader and it would go through and read all of them. Well, what happens if, you know, you lost some cards or you only got half the deck, right? How would the computer that's reading your program from these cards know that there was something missing? Well, it would know because it did not see the statement end at the very end of your program. So this is really just something for the assembler. It's one of these assembler directives, and it doesn't do anything as far as putting code into the CPU's memory. It's not an instruction. It doesn't actually execute when your program is running. It's purely just kind of, it's a period on a sentence, basically. Right? You write a sentence, you put a period at the end so that people know that's where the sentence ends. Well, we put end at the end of a program, tells the assembler that's where the program ends. But after it sees that and it says, okay, I got the whole program, it doesn't do anything with that. So if you write a program and your last statement says, you know, something like, you know, move W register into port A, and then you say end, well, that'll assemble fine, it will load fine, it will probably simulate fine, but in reality, after this statement executes, what's the CPU going to do? What do you think's the next thing that happens after that move WF?
There's just absolutely nothing?
Well, almost, except that there's never nothing, right? Our program memory always has bits in it. But are those bits all zeros? Are they ones? Are they left over from some other program? Really no way to know. So after it executes move WF port A, it's going to do something. But in particular, it's not going to stop because we had end in our program here. Remember, the end completely disappears when we assemble the program. And so we haven't told it what comes after this. Whatever happens to be in the memory is going to still be in there. And we don't know what it's going to do. So there's a few possibilities. It does crazy stuff. And our LEDs blink and our motors spin and we have no idea why. Right? Or you know, maybe it does something harmless. Maybe it goes into a loop. Or it goes all the way to the end of the program memory. And when it gets to the end, guess what? It goes back to the beginning and starts executing our program again. So usually when we're writing a complete program, we'll do something at the end. For example, we might say branch to the top, where top is, you know, some place in our code where we want the code to loop. Right? So for lab 2, you do a bunch of setup. You set up your tris and your adcon 1 and so on. And then remember we drew a flowchart with these arrows going back to the top. That's what this branch would do. So it goes back up and it starts, you know, checking the inputs, see if they change and so on and so forth. Sometimes we want our program to do something, you know, from top to bottom, and then we don't want it to do anything else. And so there we can usually put something at the end like a label called done with a statement branch to done. But we don't always do this. We don't always do this, right? We do this if we know that when our code up here finishes, we want our CPU to basically stop, to just sit there in a loop forever and do nothing. We do this if we know that when we finish our code, we want to go back up to the top and do it again. But you got to know what you want the code to do before you decide whether to do this or that or something different. But those are two things you'll typically see in a lot of microchip code. Is one of those two behaviors.
I just have a quick question.
Yeah.
So if you don't put branch top on the bottom of your loop, it will just continue cycling back to the top of the loop, essentially. Is that what you're saying?
It will continue with whatever happens to be next in memory. And on a simulator, I think it will basically just execute no ops and then go back to the first line of your program. But on actual hardware, all bets are off. It's going to do something very unexpected, most likely.
Okay, thank you.
Yeah.
What does the BRA mean again?
BRA is branch.
Oh, okay.
So that's table 20-1. There's a set of control instructions or control operations. So BRA is the unconditional branch. All of these are branches if particular bits in the status register are set or not set. So if the carry bit is set, BC will branch. If the carry bit is not set, branch. If no carry, will take the branch, and so on. All right, cool. Other questions?
Is it normal to set up a function like you described where if we need to execute a function if this values to zero, so like branch if 0, and then we go to this block that calls another block so we can return and the CPU remembers where to go?
Right, right.
Okay.
And so if we flowcharted that, right? So if x is equal to 0, call function 12, right? So we would come down here, and here's a decision block. Is x equal to 0? And if it is, call function 12. And if it's not, just keep going. And there's you know, this is unambiguous. This is what we want to have happen. But when we actually try to write it in assembly language, right? Since we're using these, you know, branch if 0, branch if not 0, how you write this flowchart can make a difference, because we could also write this as follows. Is x not equal to 0? And if it is, then we're just going to come through. If it's not, then we're going to call our function. Right, exactly the same behavior, but here we're seeing if something's equal to 0, here we're seeing if it's not equal to 0. So how would we code this in assembly language, right? So we've done something to set the 0 bit, right? We just did an increment or an addition or something like this. So we could say, you know, branch if 0, do the call, and do the call would say call function 12. And then what do we do after that? Well, we want to come back to here, right? So I don't know, maybe I'd put a label, you know, label 2, and then down here I'd say branch to label 2. All right, so branch of 0, do the call. That's checking this condition right here. And if it's 0, we're going to come down here. We're going to make our call, and then we're going to branch back to whatever that next statement was. If x was not 0, this branch is a no-op. It doesn't do the branch, and we just fall down here. So this point in our code is what we're calling L2, that point in our flowchart. But, you know, when you write this out, it's like you're coming down here, and you pop over here, and then you make a call, and then you make a return, and then you come here, and you do a branch, and you come back over here. And this is what's called spaghetti code, right? This is the reason that we don't get to use go-tos in our C programs. Because mostly in the 80s, people started realizing that having all of these branches makes code really hard to follow, really hard to maintain. And so in higher level languages, C, Java, Python, etc., we don't say goto, we don't say branch. We put our code inside these structures, these if blocks and loops and things like that. But this is what's going on under the hood, right? And if we tried to code it like this, we could do something like this. Branch if not 0, skip, call function 12, and then here skip. And so we've set our status flag based on some operation, right? And now we say if this is not 0, right, then we're just going to skip the call. We're just going to jump down right here. If x was equal to 0, we're not going to take that branch, and so we'll go ahead and we'll call the function. And when you're going back and you're working on your code and trying to figure out what it does, right, this is a little less confusing, a little less spaghetti ballish, right? We check our condition, and if we don't want to make our call, we just, skip over this instruction and come down here. If we do want to make a call, we skip the branch, right, and we make our call.
It seems like the labels would become a mess, though, right?
So you need better labels than L2 or function 12. Skip's not a bad label, but yeah, you want to pick reasonable label names. So, if this function was supposed to change the output, I might call this label "Don't change output," right? Or I might call this "Change the output," right? So that the code reads a little easier when you go back and you try to figure it out. All right, let's see. So question on homework questions 23 and 25. So yeah, this is preparation for lab 2. So suppose you want to read a 2-bit number from pins 8 and 9, where 8 is the least significant bit, 9 is the most significant bit, and then copy that 2-bit number into WReg. All right, so let's do this as a class. So part 1, how would we set up the I/O subsystem to read from pins 8 and 9? What would we have to do? So I'll put the comment in my code. Prepare to read pins 8 and 9. And so reading from a pin means there's a voltage level applied to the pin, and we want to figure out what that voltage level is. Is it 5 volts or 0 volts? So someone said tris B. How do you know it's tris B? It is tris B, but how do you know it?
That controls B.
How do we know we're interested in B and not A?
I said it was tris A, but I don't understand the difference.
Okay, so read the pin out, someone said. So pins 8 and 9 are RB0 and RB1. So let's go to the data sheet. And let's look at the pin out. Pin 8 is RB0, pin 9 is RB1. So that tells you that you want port B. So let me make a note here. Pin 8 is RB0, pin 9 is RB1. So RB, those correspond to port B and tris B. If we were using something like pin 1, which is RA0, then we'd be interested in port A and tris A. So port B, tris B go together, port A, tris A go together. All right, so we do need to set up tris B. And what do we want the bit pattern of tris B to be?
They're meant to be red, so they have to be ones.
They have to be ones because we're reading.
4 zeros, 2 zeros, and 2 ones.
Cool. Or, we could have done this. Or any values we wanted up here. But the important part is those 2 bits need to be ones, because that 1 says RB0 is an input. And this one says RB1 is an input. All right, so that's tris B. So let me make some notes here. So we want binary. We want that to go into tris B. Is there anything else we need to set up to prepare to do I/O on these pins?
Don't you have the clear port B?
We could clear port B. Cool. Got one more thing you want to do. Anybody remember? There you go. 7F goes into ADCON 1.
I had a question about AdCom 1.
Yes.
So, I know we didn't talk about it yet, but I just had a kind of a guess when I looked at 7F on a programmer's calculator, and it looks like it could be a number, but the sign bit is 0.
Mm-hmm.
Would this be why we're not getting negative numbers when we roll over?
That could be the case in some other situations, but it's not part of what's going on with ADCON 1. ADCON 1 is we'll dig into this in several weeks, but let me not make it overly mysterious. If you go down to the end of this and you look at the special function registers and you look at ADCON 1, and we have to find it, of course. So here's ADCON 1. From this picture, bit 7 is grayed out and has a dash. It means bit 7 is not really a part of this register. It doesn't have any meaning. But these other 7 bits, pin configuration 6, 5, 4, 3, 2, 1, and 0, those all have meanings. And what we're doing, as someone just said in chat, we're indicating whether each of these 7 pins is going to be used for digital I/O or analog I/O. And all we know about so far is digital I/O. And to make these things digital ports, we have to put a 1 in each of these 7-bit positions. So that's a 1, 1, 1, 1, 1, 1, 1. And it really doesn't matter what we put in this bit here. So we could just put an FF in and everything would work exactly the same. But we put in the 7F because it's kind of convention when you don't care about a bit value. A lot of times we just put a 0 in. So that's why it's a 7F instead of an FF. But you're right, that is where the sign bit would be.
I'm a little confused about AdCon and what it has to do with setting up the pins, because I thought it was just tris and port that had to do with it.
Yeah, but then there's this magic register that I mentioned. We just always set it equal to 7F until further notice. And it has to do with the fact that these pins are so multi-purpose. RB0 is also AN4. That's bit 4 of an analog input channel. RB1 is also bit 5 of an analog input channel. It's also a transmit register, it's a clock register, it's an interrupt input pin. These things have multiple purposes, and so one of the things we have to do when we want to do any I/O is set that 7F into ADCON 1. And it's saying we're not going to use AN4, AN3, AN2, AN5. We're going to use these RAs or RBs on these pins. So ADCON 1 says we're doing digital I/O. Tris A or B says we're doing input or output for each bit. And then port A or B is the actual bit value that we're reading or writing. So it's kind of like a hierarchy of instructions.
Another question.
Mm-hmm.
When it comes to port B, is it okay just to also copy the number onto port B, or does it need to be cleared beforehand? Does it matter?
I don't think there's any reason you have to clear port B. but a lot of the code does it, and I have seen a few places online where people say it's helpful to clear the port first. The only reason I can think why it's sometimes desirable is we like to know what the values are coming out of our pins, and so we clear it in the beginning to make sure we know that there's zeros coming out. But I don't think that's like particularly valid, because maybe 0 is a really bad value to have coming out. So I mean, I'm not worried if you don't clear the port to begin with. But a general file register, if you want it to have all zeros, you've absolutely got to clear it, because general registers, there's no way to know what the value is when you power up the CPU. All right, so Shaw, you would set up the I/O subsystem. So we go ahead and we maybe clear port B. We move that bit pattern into W. Move WF tris B. Move 7F into W. Move WF into ADCON 1. That prepares the I/O subsystem. And then how would you copy those pins values into WReg? So how do we read these two bits into the WReg?
Just move that specific binary number to reg?
Well,
LW.
So we want to read from port B, right? So it says, how would you copy those pins values, pins 8 and 9? How would you copy the bit values from those pins into WReg?
Move F and then comma W.
Move F what?
Move F port B.
There we go.
Comma W.
So this says read from port B and copy the value you read into the W register. Well, what's the value it's going to read? I don't know, but the least significant bit, bit 0 of the value it reads, will be based on the voltage applied to pin 8. And bit 1, the next least significant bit of port B, will be based on the voltage applied to pin 9. So if pins 8 and 9 are connected to ground, the number I'm going to read is going to look like this. I don't know what's going to be in these upper bits, because these come from other pins, and I don't know what those other pins are set to, but this will always come from pin 9, and this will always come from pin 8.
I'm a little confused because we cleared port B, so wouldn't it read not the number that is currently the wrong number?
So the funny thing about clearing is it only works on bits that are set to be outputs. If I set this bit up to be an input bit and I try to write a 0 into that, it's ignored. Right? The value of this is always based on the voltage applied on pin 8 if this is an input pin. So this is what tris B is all about. If I set tris B to all 0 so that these would be outputs, then when I clear port B, yeah, those are guaranteed to be zeros. And if I connect pin 8 to 5 volts and I've written a 0 to it by clearing it, I've created a short. But if I set this pin to be an input pin, then when I clear it, the clear is ignored. If these are output pins, it'll clear those bits, but these bits don't get changed by the clear. So if I connect pins 8 and 9 to 5 volts and I read port B, those two bits will read as 1s, even if I've cleared them out.
So basically we've just made a link to it for it to be able to read it.
Mm-hmm. All right, so we can read, copy the pins values into WReg, and then it says that WReg is value now exactly the same as the 2-bit number that you want. So connect these two pins to 5 volts, and let's move port B into the W register. Is WReg equal to this? Possibly, possibly not. Right? WReg is this. We know that these two bits will be 1 if we've connected pin 8 to 5 volts and pin 9 to 5 volts, but we don't know what these bit values are up here. Now, if they were all set to be output ports and we cleared port B, we'll probably read zeros when we read those. But if some of those are also input ports, we don't know if those are going to be zeros or ones. So if we tie these two pins to 5 volts to try to input the number 3, right, this number, into the processor, and we read from port B into W, we may not yet have the number 3 because we've got this extra stuff up here. So how do we deal with that extra stuff? Yeah, so in chat, we use an AND operation. We use a bit mask. So if we were to AND W with the literal like this, or just the number 3, right? Each of these zeros ANDed with whatever this happens to be will force those to be zeros. And these ones, when we AND it with these bits, will leave these bits intact. So this bit mask, doing this AND with a bit pattern, will take our number that has some gibberish on the end and it'll turn that gibberish into zeros. And now, you know, if I put 0 volts on both of these, I'll read a 0. If I put 5 volts on both of these, I'll read the number 3. If I put 0 volts and 5 volts on pins 8 and 9, I'll read the number 2. And so this is what you're doing in lab 2, right? You've got input pins, but your numbers that you want to add are mixed together with other numbers and with things that are being output and so on and so forth. So you have to use these bit masks. So that's what this preparation for lab 2 business is about. And then question 24, we're doing pins 17 and 18. And those are also bits of port B, right? Bits 2 and 3. But when we read those, this is pin 17, this is pin 18. So when we copy from port B into W, pin 17 is here, pin 18 is here, we've got other stuff here, we've got other stuff here. We have to use a different bit mask to basically make all of these things 0 and just leave us with 2 bits here. And then if we want to do something useful with that, we probably want to rotate it twice. Move those 2 bits over to here. And then that's where this suggests, you know, saving that as a second number. Does that make sense? So this is basically the guts of the code for lab 2. Let's see, question, how do we put the output onto the pin we want? Well, you can write your output to the entire port, but you have to write all 8 bits at once. And so if we set certain pins to be input pins, and we copy from, say, W to port B, any pins that are set to outputs, those bits will be set based on the value that we wrote. Any pins that are set as inputs will ignore the values that we wrote. But you write all the bits at the same time, basically, or you try to write all the bits at the same time. So you take an 8-bit value, you copy it to port B, and wherever tris B says those are outputs, those bits go to the output pins. Where it says they're inputs, those bits are ignored. All right, talk about question 25. So 2 sections of code. The first one puts a 3 into tris B, copies from port B to first num, and then puts a C into tris B, copies from port B to second num. The second version of this code puts an F into tris B and then reads from port B into first num and second num. So question is, what's wrong with this version of the code?
Well, it I don't think it will throw an error at you, but I think it will be dangerous in real life because you're trying to read from the first two pins on TRISB first,
Mm-hmm.
and then after that you're trying to read from four pins.
Mm-hmm.
Um, Wait a minute.
So
I
let,
read this as you change them to outputs, and then that would be dangerous because you're trying to read from something, then you're trying to output from something on the same line, and then that could be dangerous in real life because
okay,
you could have inputs come in and
perfect.
enter the output pins.
Perfect. And we got some other answers in chat that are saying the same thing. So this moving a 3 into TRISB, um, think about this. All right. So there's what TRISB looks like. If we move the number 3 into TRISB, what does 3 look like in binary? It looks like this. As soon as we set TRISB to this value, these two pins, we're saying those should be outputs. Right? We're setting TRISB equal to 3 because we want to read from these two pins. But do we also simultaneously want to write to these two pins? Definitely not. But if we load this value into TRISB, these two zeros say these are outputs. And now the chip is going to take whatever the value of port B is in these two bits, and it's going to drive the voltage on pins 17 and 18 either high or low. But since pins 17 and 18 are actually connected to switches, or some other input, we have the potential to create a short here. For example, maybe port B happens to have 1 sitting here, and maybe our switches are closed so that these are connected to ground while we're asking the CPU to supply 5 volts to this pin that's connected directly to ground. And so that's a short circuit. And on the PIC processor, it's not a big deal. On some really nice, expensive, multi-$100 chips, this will blow the I/O port. And then you gotta mark the chip as saying, don't use RB2 or 3 because they're blown. So if we know that we're going to, at any point in time, have external values connected to these two pins, when we set up TRISB, we want to make sure we set those to 1s. If we know we're going to have, external voltages supplied to these pins, let's make sure we set those to 1s in TRISB at the same time. And remember, the initial value for TRISB is all 1s. So when we first start applying power to the CPU and it starts executing the program, all of these things are set to 1s. Every pin is an input pin. It's never going to apply a voltage to any of those pins unless we change TRISB to have a 0 in one or more of these positions. So as long as we don't inadvertently do this, no harm is done. So that's what exercise 25 was about. I was just kind of thinking about that. All right, so go ahead and send me an attendance check. Let me know you're here. All right, awesome, thank you. All right, so let's talk about Lab 1. So I've graded Lab 1 and Homework 1, posted those on Canvas. I posted them with comments. So first of all, make sure you look at the comments, okay? There are cases where there were, small issues with the homework or the lab that did not cost you points, but that I mentioned and discussed in the comments. And it's possible that if those things happen in the future, they will cost you points. So always look at the comments. Even if you get, a perfect score on the assignment, there might still be, things that didn't look quite right, or that I had some question about, but I just didn't take points off for. So always look over the comments and ask questions about them when you get your assignment back. But I gotta tell you, Lab 1 was fantastic. I was so happy with the job people did. Particularly the new experiments were great. Most people came up with some really cool experiments, and as we've said, Lab 1 new experiment is the hardest of the whole course, because we kind of had so little to work on, but people applied a lot of creativity and came up with some good experiments, so that was definitely good to see. And most people, were able to put their code in, step through it, and so on and so forth. Good write-ups, everything was typed, nice presentation, and so on and so forth. So the biggest thing that I saw that was an issue in some reports is this idea of, you've done the work. Your goal in writing the lab report is to present what you did to the world so that somebody else can try to reproduce your results. Okay, this is how science happens, right? We do science by, here's a hypothesis, here's an experiment I've concocted to test the hypothesis, here's the steps I did, here's what I observed, what's my conclusion, the hypothesis holds, right? And that's as far as we can take things in science. It's very rare that we can prove something with an experiment, but we can definitely disprove it, right? I dropped a bowling ball 100 times, and each time it fell to the ground. So, I think there's this thing called gravity. Well, we haven't proven it. It could be a dragon inhaling that pulls the bowling ball down, right? But if I drop the bowling ball once and it floats, the theory of gravity is called into question, right? So you do your experiment, and you drop your bowling ball 100 times at 100 different locations around town, and each time it falls, and it takes the same amount of time to fall from the same height, right? So this is very exciting, and you want to share this result with the world so other people can reproduce your experiment. So your lab report, or your journal paper, right, would have to describe what you did, right? What kind of bowling ball? How much did it weigh? What height did you drop it from? How did you measure how long it took to hit the ground? Did it always take exactly the same amount of time, or was there a bit of variability, but the variability was within the margin of error of your assistant with the stopwatch, right? You got to have all those details in there so that now somebody in Switzerland looks at your paper and says, I'm going to see if this is really true, and they're going to reproduce your steps. So how does this apply to Lab 1? If you say something like, after entering the code, I performed a series of steps and the code acted as I expected, well, that's a good synopsis, but that doesn't let somebody else reproduce your work. If you say I hit the run button several times and nothing much happened, well, did anything happen? Did nothing happen? What does not much happened? And then I hit this button and a few things changed. Well, what changed, right? So as you're writing up your procedure and your observations, be thinking about, is there enough detail here that somebody else could reproduce this work? All right, but I'm going to put a caveat on that. So with Lab 2, you can assume whoever is reading your lab report understands, Engineering 270 up through Lab 1. So you don't need to say, first I found a PC and I hit the power button, and then I plugged it in to make sure it wouldn't discharge, and then I found the MP-Lab icon and I clicked it with the left mouse button, right? You don't need to go down to that level of detail. So there's a high-low game to play of too much detail and your report is, War and Peace. Not enough detail and somebody can't reproduce your work. So with Lab 2, for example, you can assume somebody knows how to run MP-Lab, knows how to enter the code. If you show them a copy of the code in the disassembly listing, they can type the code into their MP lab, right? If you say I set up a watch on locations 80, 81, and 82, you can assume now that they know how to do that, right? Lab 1, you might have talked about that in the procedure, but Lab 2, you can assume they know how to do that. If you're going to set up a stimulus on RB2 and 3, you need to say I set up a stimulus on RB2 and 3 to toggle, or to set high, or to set low, right? But you don't need to go through, I clicked on this button and I went to this menu and this and this, and then I hit this drop-down box, right? So the proficiency of the reader should match what your proficiency was before you did this lab. But make sure you explain, you know, what stimulus did I set up? I set up a stimulus on RB0, 1, 2, 3, 4, 5, 6, and 7. And I set up a watch on port A, and so on and so forth. Does that make sense? So it's like finding the right level of detail.
So, speaking of that level of detail, I had more of a question on the flowcharts.
Yes.
So I noticed back on our example last week when we had a conversation about flowcharts and how we should set up each block, that we wanted a certain level of detail, but we didn't have to go too far into detail.
Right.
The first part was like init adcon 1, init tris B, init tris A, and that all makes sense, right? But would using actual instructions like MOVF port B to reg, would that be going too far into it?
That's probably too much detail for a flowchart.
Okay.
And it's actually kind of counterproductive, because if I say MOVF 7F, adcon 1, I've got to figure out what adcon 1 is, and so on and so forth. If I have a block that says, you know, set up I/O ports to do input from these pins and output to those pins, right? Well, reading the flowchart, now I know exactly how the thing is set up. I don't know what instructions will cause that to happen, but that's the job when you're going from the flowchart to writing assembly language. So this is definitely a higher level view of what's going on, and you're trying to capture more kind of the algorithm, right? What are the steps that we want algorithmically? We want to read the two numbers, right? Read a number, break it into the first num. Read the input, break it into the second num. See if they've changed. If they haven't, go back to the beginning. If they have, add them together, send that to the output, go back to the beginning. That kind of thing.
Also, would it be okay to use like a flowcharting program that I use for like other trying to work out logic for other programs? I just draw a flowchart in this program.
Yeah, that's fine.
Okay.
I'm totally happy with people drawing flowcharts by hand. Just try to do it legibly. Don't make me follow a maze of lines, but you know, just from top to bottom. I'm totally fine if you just do it by hand. But if you want to use software to do that, that's totally cool too. Well, let's take a look at Lab 1, just in terms of what it does. So I copied the code for Lab 1 onto Canvas, and some people tried to copy and paste from there, and it didn't work. But you can download that file. That's just a plain .txt file, and if you download that, it should open up, and you can copy from, you know, this code inside WordPad or something, and paste it into here. So here's what the code looked like. And the instructions basically had you set a breakpoint at this clearF, set up watch points for port A, port B, and W reg, and set up a stimulus for RA0 with an action of toggle. And then we can go ahead and build this. And then if you want to simulate it, we can just hit this little debug program, or we can go to the debug menu and say debug. And it says, you know, launching, initializing simulator, program hit, breakpoint hit at line 23, which is this line that had been highlighted red. So when you say run your program, it starts from the beginning, and we have this origin 0 statement. So this clearf is stored at location 0, and you can see that in the disassembly listing as well. And it always stops when it's about to execute an instruction. So it has not executed this clearf instruction yet, but it's about to. And at this point, I can use this button here to say step, and this will step my program one instruction at a time. So if I hit this button, it executes that clearf on port A, and now it's about to do clearf port B. And if I execute that, now it's about to move 7F into the W register. And if I look down here, W register is equal to 0. That's this bottom line down here. If I step through this instruction, it turns red and tells me, hey, the W register is now 7F. That's the result of doing this move LW 0x7F. And then it's going to put move WF into addcon1. And if I hang out my mouse over these different variables like addcon1 or port A, the simulator will sometimes show me a picture of what the values of these bits are. And so if I look at addcon1, it tells me that it's equal to 0. I can't point with my mouse right now because it'll go away. Oh, no, I can. So it tells me that addcon1 is 0. Well, I'm about to set it equal to 7F by doing this move WF. So if we step through that, and now I look at addcon1, you can see it's got a bunch of 1s in it. That's the 7F that we just loaded. So you can step through this and you can kind of see what's happening. But the main observation that people made for the lab is that if we keep doing this, eventually we get to where we're looping. And my registers are all equal to 0. And I just keep looping, and that's pretty much it. It just sits here at this loop. Well, that's probably a good observation to make in your lab report, right? So I hit the step button multiple times, and it moved through my code until it got to this line down here that says go to loop, and then it just repeated these 8 or 9 instructions over and over and over again. And nothing seemed to change in port A, port B, or W reg. So what do you do then? Yeah, go ahead.
Okay. So like earlier we were talking about branch top. I see on the bottom of this loop it says go to loop. Is that like the same thing?
Go to and branch are basically the same.
Okay. Cool.
We'll talk about the differences later, but you can use them more or less interchangeably.
Go to is basically just or B and Z. Sorry, branch instructions are basically conditional go-tos.
Just a plain BRA is an unconditional go-to. It's an unconditional branch. The difference is go-tos take more memory to code, but you can go to anywhere. Branches, you can only go to places that are pretty close to where you are now. You can go like plus or minus a few hundred instructions, maybe.
Really? There's differences in how much memory they take?
Yeah, so go-to is one of the few instructions that actually takes 2 words, 32 bits to store, whereas branches only take 16 bits, just like most other instructions.
Interesting.
And if we look at the disassembly listing, that's not what I wanted. There we go. If you look at the disassembly listing, this go-to is stored at location 002C in program memory. It's followed by a no-op at location 002E, and then the next instruction, this MOVF, is stored at location 0030. So these 32 bits all correspond to the go-to, basically. And a call is the same way. A call takes 32 bits, whereas most of these other instructions take 16 bits, 16 bits, 16 bits.
Would anything that requires 2 cycles be like in that 32-bit category, like MOVF?
MOVF also takes 32 bits, and that's pretty much it. MOVF, call, and go to are the three main ones.
Got it.
All right, so what could you put in your lab report, right? Under procedure, I hit the step button, a gazillion times, and after it got to, this go to loop, it just looped between here and here and here. And it did that forever and ever. Well, so you're also told to set up a stimulus button and fire that. So now I fired the stimulus on RA0, and the next time I stepped, hey, port A changed value. It changed from a 0 to a 1. And then I stepped a bunch of times, and this time it went somewhere different. It jumped down to a new section of code called INCL. And it did some stuff there, and some more things changed. In particular, port B changed from a 0 to a 1. And then I clicked some more, and it went back to its old self and just started looping again. And it did that forever and ever. So I hit the stimulus again, and I stepped it a bunch of times, and it jumped down to INCL again. And as it went through that, port B changed to a 2. And then it went back and it started doing its stuff again. So this is your creature in a petri dish, right, that you're looking at under a magnifying glass or a microscope, and you're hopefully humanely experimenting with it and seeing what it does. It looks like when I fire the stimulus, the code will shortly thereafter jump to this increment L section, and port B will end up having a new value, incremented by 1. And then it goes back to its old behavior, right? So that's kind of the more interesting part of what this code does. Yeah, it sits here and it loops forever, but every time you fire a stimulus, it jumps down and it does this increment L. And then port B changes, and then it goes back to looping again. So that's all, stuff that you experiment, you observe, you write it up, and so on and so forth. And you put it in the lab report. And then lab 2, you're trying to make something that adds two numbers together so you know what behavior you're looking for. So hopefully in lab 2 you've got, a good description of what you did and how you tested it and what you observed and so on. Now sometimes it's nice to put in screenshots, but again, lab 2, we can assume the person understands how to look at the values of variables that are being watched, how to set a stimulus and so on. So you may not need screenshots for lab 2, right? But you definitely want to describe in detail how you're testing your code, what it does, what happens as you step through the program, what happens when you change an input value, what outputs change, how does the code change, and so on and so forth. All right, does that make sense? So as I say, really happy with Lab 1. I think people did a great job with this. And so keep doing it for Lab 2 and onward. All right, let's look at homework 1. So homework 1, I basically graded questions 3 through 6 and 11 through 15. So didn't grade 1 and 2. 3 and the homework looked great, right? Most people nailed this code perfectly. If you lost points on here and you're not sure why, definitely come and ask. But looks like people understand how to use the W register as a temporary, right? How to use the comma 0 after these byte instructions to put a result into the W register. And it looks like people understand the difference between saying move F comma 0, and move WF. And that's all kind of the trickiest part of dealing with the W register. So no concerns on any of that. I did not grade questions 9 and 10, but you will see these questions on exams. So my suggestion, if you're not convinced that you did these correctly, try them in the disassembler, right? If you converted these into assembly language, go into MPLab and type each of those instructions in, assemble your code, look at the disassembly listing, confirm that these are the bit patterns you got. And then for these, right, just type these instructions into MPLab, go ahead and assemble it, look at the disassembly listing, see if the bit pattern that it gives you matches the bit pattern that you came up with. Question 10 is on the new homework, homework 3, so that's playing with the access bit. And then the literal questions, no issues I saw with that in most cases. So, and it's tricky keeping straight the idea of a literal versus a file register. If we're talking about a file register and we say, 0x02, we mean file register 2. If we're using a literal instruction, we say move LW 0x02. We're talking about the number 0x2, right, getting loaded into W, as opposed to the contents of register 2 getting loaded into W. But it looked like people had the right idea of that. So take a look at the comments and ask questions if you have any on there. I'll grade homework 2 hopefully today or tomorrow, and we'll talk about homework 2 on Thursday. And then homework 3, which is due a week from today. So a few details on that. Okay, question 10 is figuring out what the access bit is. So that's just that A bit mysterious stuff. 32 and 33. So I say determine the PC of each instruction executed. What I mean by this is tell me the address in program memory where each of these instructions would appear. Okay, I'm not asking where this call instruction goes or where this branch instruction goes. I'm asking what's the address in program memory where this increment file register instruction is stored. And we can do that one as a class. What's the answer? Where is this INCF going to be stored in program memory?
$20.
20. Why is it stored at 20?
Because the org directive tells us to start at 20.
Because the org directive tells us to start at 20. This is what org does. It says the next instruction you see gets stored where? Location 20. Well, here's the next instruction. It's going to get stored at location 20. What about begin? Does this get stored in memory? Now, this is homework 3 we're going over. So this isn't due till next Tuesday. Yeah, no problem.
Begin would start at 22, right?
Begin would start at 22. Begin itself is just a label. It's an assembler directive of sorts. It doesn't actually get stored, but it says, if I talk about the word begin somewhere, I mean, the location where this call is stored. And yeah, this call would be stored at location 22. How do we know that? Because if you look at the data sheet, INCF is 2 bytes, 16 bits. It starts at location 20. It's stored at location 20 and 21. The next free location is 22. That's where the call is going to get stored. So you just kind of work through the code like that. So work on those and ask questions. But that's the goal here for 32 is figure out where in program memory each of these instructions is stored. You don't have to translate these into binary. You just need to know where they're stored. And then 33, same question, but instead of this branch to begin, imagine this says go to begin. And then just redo the question. Where do each of these instructions get stored? And then 34 through 40. So these are some of the stuff we're going to be working on today. And Thursday is working more with these conditional statements, these conditional branches, and so on. So here's some exercises in, subtract 1 from x, and if it's equal to 0, go to, a label called somewhere, right? So writing pick code for these. And for these, I want you to write flowcharts for each one, and then go ahead and write some assembly language code. And all of these questions, right, I don't need disassembly listings. I don't need to see this in MPLab. You can put it into MPLab if you want to test your code and simulate it and so on, but all I'm looking for is just a typed up set of instructions, right? So 35, draw a picture of the flowchart and then just type out the instructions. So decrement file register X and then branch if 0 or branch if not 0 or whatever.
So for all pick code that we're going to write on for this homework, you want us to do flowcharts, right?
Yes, please.
Okay.
If we encounter a loop on a flowchart, should we still include the end at the end of it? The line doesn't go to it?
So you don't need to put an end statement if you're just writing a small set of code to implement something like this. I don't need to see the end statement. I don't need to see the config WDT equals off, all of that stuff. I just want to see sort of the code corresponding to this. So yeah, you can leave end off of the end.
Oh, I meant the flowcharts though.
Oh, the flowcharts. Yeah, so you can put the oval with end at the bottom just to say that's the end of the flowchart for this section of code. Even though it's not the end of your program. Again, it's just so I know, do I have to go to the next page to find a continuation of the flowchart, or is that the whole flowchart? So the start and end are just kind of like capital letter and a period. And then 43 through 48, so we're going to talk about this today and Thursday, about coding up branch and go-to instructions in memory, and that's just going to be some nitty-gritty stuff, and that will make more sense out of these questions. Let's see, where are we on time? We are after... All right, let's take like about a 5-minute break. Send me an attendance ping, even though I know you're here, but I want to be consistent about this. So send me an attendance ping, and we will come back in about 5 minutes, and we'll start looking more detailed at these branch instructions. All right, we're back. All right, let's dig a little deeper into this business of conditionals. And we already played with one of these in the beginning, looking at that kind of flow chart. But there's a few gotchas that can pop up with these branches. And as I mentioned in the homework, I want you to stick with branch if 0, branch if not 0. I don't want you using any of the skip instructions. So there's test file and skip, there's compare file and skip, there's all these skip instructions. I'm going to tell you not to use those for now. We'll talk about them eventually, but skip instructions are extra confusing. And I think I've had one student in the several years I've been teaching this who was able to consistently use skip instructions correctly. And conditional branches, much harder to go wrong with. And if you know how to do your control logic with branch of 0, branch of not 0, you can always figure out how to do it with skip statements after that. So I want to stick with branch of 0, branch of not 0. So let's look at let's look at some details of this. So we have the status register, right, which has a bunch of bits in it. One of those bits is called Z. So we can think of Z as a flip-flop. And it's a little backwards. If Z is equal to 1, that's how the system records that it saw a 0. If Z is equal to 0, that's how it records it saw something that was not 0. So we got some flippy-floppy right up front, right? 1 means 0, 0 means not 0. But don't get tripped up by that, because we don't usually look at these bit values. We just use a statement like branch if 0 or branch if not 0. And if we don't think about this as saying branch if the 0 bit is equal to 1, we're not likely to get confused. So that's what's going on, but we don't really need to think about it. We're just going to think, branch if the last thing we did was 0, or branch if the last thing we did is not 0. And so if we have a statement like, if x equals 0, then let's, go to a section of code called haha, right? That's really easy to code. We just say branch if 0, haha. If we wanted to say if x is not equal to 0, go to he. We could just say branch if not 0, he. So those are pretty straightforward. But more often we have something like this: if x is equal to y, go to, something that does some stuff. And so how do we figure out if x is equal to y by using a BZ or a BNZ?
We could do a subtraction operation with x and y and evaluates to 0, BZ, whatever, right?
Perfect. So seeing if x is equal to y is the same thing as saying if x minus y is equal to 0. Or if y minus x is equal to 0. Right? Either way. So what we can do here is we could do something like move x into the W register and then subtract the W register X from file register Y. And I honestly don't know if this is going to do X minus Y or Y minus X, but it doesn't matter, because we're just interested in are they the same or not. But it's really important when I do this, I save the result back in W. Why? Because I don't want to change X, I don't want to change Y. If you wrote a C program which said if X equals Y, do this, and after you were done, Y had a different value, you've got a buggy C compiler, right? Nothing in this statement says change the value of X, change the value of Y. So one of the things we use these temporary registers for, this W register, is to be able to do a calculation where we don't want that result to go back and change our actual operand. So we put X into the W register, we subtract it from Y, but we put the result back into the W register. And now we can say branch if 0, and that 0 bit is based on the results of this subtract instruction. All right, and remember table 20-1, when you look at these instructions, subtract WF, there's a column over here which tells you which flags in the status register are updated. Z is listed in here, that means subtract WF will update the 0 bit. And so it's totally valid to do a branch of 0 after a subtract WF. But for example, MOVF, which moves from one file register to another, does not update any status bits. Move the W register into a file register, does not update any status bits. Multiply the W register by a file register, does not update any status bits. So you always want to come back to your data sheet and make sure that if you're doing something like this, I'm going to subtract and then I want to branch based on whether that subtract was 0, go to your data sheet and make sure this instruction touches the 0 bit. That can be like a multi-hour adventure trying to debug code simply because you're using an instruction that doesn't touch that bit. And that can be really hard to find what the issue is. Alright, so we can do this to see if X is equal to Y. Similarly, if we wanted to say if X is not equal to Y, so we can do the same thing and then just do a branch if not 0. And as a flow chart, right, the flow chart's pretty straightforward. We have a condition. If the condition's true, then we're going to go to another block of code that we're just going to call stuff. Otherwise, we're just going to flow through to whatever the next statement is. But let's make some more interesting flow charts. So let's do if X is equal to Y, then sum should be equal to 0. So what would this look like in a flow chart? So
Wouldn't it be 2 equals for...
if we're doing C or Java or Python or an actual language, yeah, we want 2 equal signs. And I should probably get people in the habit of that, but I'm being like something today. But yes, you're right. All right, so pretty straightforward. If X equals Y, then we're going to come over here, we're going to set the sum equal to 0. If it's not equal to Y, we're just going to fall through. So how can we code that in assembly language? Let me put the start here. So there's my comment. Is x equal to y? And there's a lot of different ways to do this. So somebody start us off. What should we do after we've done this subtraction?
We could do a branch if not 0.
Okay. Where should we branch if not 0?
We should branch over to sum equals 0.
Okay, give me a label.
True.
Okay.
True 1, I guess.
Okay. What's our next statement?
And then we would go to the block where sum equals 0 and we assign. We would.
So like clear F sum?
I guess we could do it that way. I was thinking like move literal 0 into reg and then move reg off. Move WF reg over to sum.
Okay, that would work too. I'll just go ahead and do a clear F just. But with a comment, etc., because you could put a 0 into W, put W into sum. A inexpensive compiler would probably do it that way. It would put a 0 into W, copy that into sum. A slightly better compiler would say, oh, I can just clear, but they charge you more for that. All right, and then what do we want next?
Then we would just. I guess we'd have to put a label where the conditional is.
Mm-hmm.
Return just after the conditional, and we return to that label by doing a BRA or go to the label after the conditional, right?
Well, I think it's more straightforward than that. So what does this do for us? What if we put a label true 1 right there? So we subtracted x from y. We said if it was not 0, let's jump down here. So that's this part of our flow chart. If it is 0, though, that means x equals y. We're not going to do the branch. We'll go ahead and we'll clear our sum, and then we'll come down here. We're back to this part of the flow chart. So I think this is all you need to implement that. Does that make sense so far?
I think so.
And I might change the name of this label to like not equal. And now if I read it, it's like, let's see if x and y are the same. If they're not, if their difference is not 0, I'm going to go to this label called not equal. Well, this is where I branch to if x is not equal to y. Otherwise, I clear my sum, do that block, and then I just kind of fall through to not equal. And if I had more things I wanted to do in here, I could do those things here. And all those things get skipped by this branch if not 0.
This is how a compiler would do it for an if-else in most cases, right?
Possibly. There's a lot of ways to do this. So how would we do this with a branch of 0? Suppose it's BZ day, and so we're required to only use branch of 0 instructions.
For branch of 0, we would jump to some label equal, which would contain the clear f sum.
Okay.
And
So
then continue from. Yeah, branch doesn't have a return function, does it?
doesn't have a return function. So this flow says, you know, if these are equal, we want to come down here and do the sum equals 0. Well, let's say if we branch equals 0, let's go to you know, r equal, or let's call our label x equals y. And x equals y would go somewhere. And what I would do here is I would say clear file register sum. And then I want to branch back to whatever this point is. So maybe I'll call that not equal. And that might be here. So do your subtraction. If the result is 0, come down here, clear the sum, and then go back up here. And you got to be careful, because if I'm not careful, when I get back up here, I'm going to fall down and do this next instruction, which says clear the sum, and the sum is going to get cleared even if x was not equal to y. So now I might need something like branch to continue. And maybe continue goes here. And now you see why it's called spaghetti code. So if x is equal to y, we'll jump down here, we'll clear the sum, we'll branch back to not equal, and we'll branch down to continue. So that's that part of the loop. If x is not equal to y, we'll skip this branch, and this will just say branch down to continue. And we'll come down here. But can we clean this up a little bit? Particularly that case where they're equal. What does this branch do? Where does this branch go?
It goes up.
It goes to not equal, and what happens when I get to not equal?
I just go to continue.
Goes to continue.
You could just put the. You could like replace just not equal with just a go to, and then move the x eqy above. Or no.
Well, so yeah, there's a way to do that. The way I was thinking was we could just say, you know, branch to continue instead of branching to not equal, and have that branch to continue. But if we're going to branch from here to continue and continue to the next statement, we don't need to branch at all, so we can actually just take this out completely. So what's the flow here? Calculate x minus y. If it's the same, if x was equal to y, come down here, clear your sum, and then just continue with your code. But if x minus y was not 0, jump down here, skip over the clear instruction. And since we're not branching to not equal, we don't really need this label here either. So this cleans up nicely. So move x into w, subtract w from y, put the result in w. Comment, is x equal to y? Branch of 0, x equals y. So we're going to branch if x is equal to y. Otherwise, we're going to say branch continue, which says, you know, that's where we're going to go if x is not equal to y. At the label x equals y, we're going to clear sum. And then continue is whatever is going to happen after this little block of code has finished. So
That's still spaghetti code though, right?
it's a little spaghetti-ish, but it's not too bad. So look at our first case where we did a branch if not zero. Do this thing. If we don't want to clear, let's just skip over the clear and come down here to not equal. Here we're saying if we want to clear, jump down here to the clear. Otherwise, skip over that clear instruction. So it's got one extra branch, but it's not too bad. It's still kind of flowing from top to bottom. So as you write these things, right, be aware that there's different ways to write the same instruction. And sometimes, you know, for this particular thing, a branch of zero is going to make your life a little easier. Or maybe, you know, in this case, a branch of not zero is going to make your life a little easier. And feel free to experiment with that. Right? This is a fundamental component of programming. And being able to think about these logical conditions from different directions and frame them in different ways, that's a really, really powerful thing to be able to do. That will help you a lot with not just this, but with all programming down the road if you're CS major. And then sometimes it's going to be spaghetti-ish no matter what. So if x equals y, then let's clear sum. Otherwise, let's increment sum. So this might be a flowchart for that block of code. So let's calculate x minus y. Well, it's going to end up about the same whether we do BZ or BNZ, because we've got two separate branches we have to follow here. So here's a typical way to do this. Branch of 0, x equals y. If we don't branch, what does that mean? It means x is not equal to y. It means this subtraction was not 0. So this is a really good place for a comment. Like x is not equal to y. Well, if x is not equal to y, what do I want to do? I want to increment sum. So I'm just going to say increment file register sum. Well, I need to write code for what to do if x is equal to y. And so I might write, you know, x equals y. And what I want to do here, if x is equal to y, is I want to clear sum. But there's a problem. If this is my actual code, this is not going to work quite right. So what's the big problem here? Suppose x is not equal to y, so I don't branch and I increment my sum. That's that block. What's the next thing I do after I increment my sum? Alright, I got x and y, I subtracted them, checked to see if they were equal by seeing if the subtraction was 0. Suppose the subtraction is not 0. So x is not equal to y. So I'm down on this branch. I come down to this statement which says increment sum. I've done this block. What's the next statement do? it clears the sum. That's not what my flowchart says I should be doing. It says after I increment my sum, I should flow through to whatever the next block of code is. But if I write my code like this, if x is equal to y, I come down here, I clear my sum, and I get down to the next statement. That works great. But if x is not equal to y, I skip the branch, I increment my sum, but I'm clearing my sum after that. Right? And I've seen this exact chunk of code so many times, right? So how do we avoid inadvertently clearing our sum after we've incremented it correctly? How do we avoid incorrectly clearing it? Any ideas?
You could put a continue statement at after both of the blocks, like continue one, and then after either of the two blocks, if they execute, they have to go to the continue.
Okay. So let's put a continue one here. And after I increment, I'm going to branch to continue one, which will skip over this clear instruction. Bingo, our code's working again. And then after the clear instruction, if x was equal to y, we did our set sum equal to 0. We want to go down to continue. Well, we could put a branch to continue 1. But if continue 1 happens to be the next instruction anyway, we don't even need that branch. So now the flow is the following. If x is equal to y, we jump down here, we clear the sum, and we do this. If x is not equal to y, we skip the branch, we increment the sum, and then we skip over that clear instruction. And so equal to y, we've done exactly this. Not equal to y, we've done exactly that. And in either case, we end up here at continue 1. All right, I don't know if that helps or not, but that's those programming questions on homework 3. And this is stuff you'll have to be doing in lab 3. So lab 3 is a return to the traffic light. You're going to do one more traffic light control system, and that's going to be implemented in PIC assembly language. And so it's really just going to be a whole bunch of conditional statements. So you'll be doing this a lot in lab 3 also.
Are we going to need to be working with some sort of delay for the traffic light?
Yeah, we'll need a 2-second delay, and we'll talk on Thursday how to make that happen. And it won't work very well in the simulator because the simulator doesn't understand time the same way we do. But we'll go through how to set up a 2-second delay if you had actual physical hardware, and it's pretty straightforward. Yeah,
just
yeah.
No op until you have enough clock ticks.
Exactly. So it's a structure we just call a delay loop, and it's just making sure you execute the right number of instructions to cause 2 seconds to pass, and it's pretty painless to set up, but it's a separate set of details. Alright, so change of gears here. Let's go back to looking at assembly language, instructions, and how we code them in binary. And the branch instruction is kind of goofy when you code it. So come down here and let's just look at an unconditional branch. So it says the mnemonic and the operands for this is branch to n. And the coding for it looks like this. It's 1101 0 and then a bunch of bits that correspond to this number n. So I'm just writing down the information from this line here. 1101 0, 3 ends, and then 4 ends, and then 4 ends. And I'm just throwing a bogus label in the beginning of this program called test, and then I'm saying branch to test. And I want to assemble that, and I want to look at the disassembly listing. So test is sitting right before this clearF port B instruction. So the label test refers to the location in memory where this highlighted instruction is stored. Now when you look at the disassembly listing, this leftmost column, this is the location in memory where each of these instructions is stored. So the clearF is stored at location 0. Why? Because it said origin 0. ClearF takes 2 bytes, 6A80, and so the next instruction, clearF port B, starts 2 bytes after the first one. That's location 2. Here's a MOVLW, it also takes 2 bytes. That's stored at location 4. The next instruction is stored at location 6. All right, here's the goofy thing. This instruction says branch to test. It's listed by the disassembler as branch to 0x2. And why is it written like that? Because test, remember, is a label corresponding to the address of this next instruction, which is at location 2. So branch to 2 kind of makes sense. That's the address that we want to actually branch to. But that's not how this instruction is coded. This instruction is coded as D7FD. Well, what does that look like, D7FD? So what is D in binary? Here's your hexadecimal test for the day.
It'd be 1110.
Good. D is 1101. 7 looks like that. F looks like that. And D is still 1101. All right, so 11010, that's those 5 bits. And these remaining bits correspond to N. And so N is the following number. And so it looks like our branch instruction is actually saying branch to binary 111111101. Which does not look at all like the number 2, right? So the coding of these instructions is different. And we need to go down to the actual data sheet and go down to chapter 20 and look up the actual branch instructions. And so there's our branch. All right, so we branch to some number n, and you know those n's get coded down here. Well, look at the operation. What's the operation that this branch performs? It takes the current contents of the PC, it adds a 2 to it, it adds 2 times n, and it loads the result back into the PC. So when you say branch to this thing, that's not the address you're branching to. This is the number n. And what you're really branching to is your current PC plus 2 times this number. All right. Well, what's the PC when this branch instruction is executing? That's the same as saying where in program memory is this branch instruction stored, and our disassembly listing tells us the branch is stored at location 6. So the contents of the program counter at that branch instruction is 6, and then we're going to add 2, and then we're going to add 2 times this number n. Well, now we got to figure out what is this number n equal to. And this is a 2's complement number. And is this number positive or negative?
It would be negative because the sign bit's 1.
It would be negative because the sign bit's 1. That's assuming that we're using 11-bit 2's complement notation, which we are. But it doesn't actually say that. But this is all we have. We have 11 bits. So this is the sign bit, which means this is a negative number. But negative what? Well, if you have a number in 2's complement that you know is negative, you can take the 2's complement of that to get a positive number. And then your original number was just the negative of that positive number. So this is flashback to Engineering 250. So let's take our number. Let's complement all the bits. And let's add 1. And we get this number. So what is this number equal to in decimal?
3.
Yep, that's good old positive 3, which tells us that this number must have been negative 3. So now we know that our number n is equal to negative 3. And so we're branching to 6 plus 2 plus 2 times negative 3 equals 6 plus 2 plus negative 6, which is 8, plus negative 6, which is 2. So this branch instruction is going to change the program counter to be equal to 2. And guess what? Location 2, that's the address in program memory where the instruction right after test is stored. So this branch, D7FD, will change the program counter to be back to a value of 2. It'll jump to this instruction, which is exactly what we wanted it to do when we said branch to test. All right, so this is a lot of stuff, right? This is easy for the computer to do. And it's set up in a way that makes it really easy for the computer to do, but pretty unpleasant for people to do. So when you're asked to code a branch instruction into binary, you got to go through all these gymnastics. But the punchline of this is these branch instructions are relative. They specify where we should branch to relative to the current instruction's location in memory. And this is why branches are limited in how far we can branch. Because the biggest this number can be is 1023, and the smallest it can be is negative 1024. So we can really only go forward or backward about 1,000 locations in memory. And remember, we can have 4,000 bytes of instructions. Sorry, go ahead.
But you can go much further with go-to, right?
But with the go-to, you can go anywhere you want. And with a go-to, we actually store almost exactly the address in memory that we want to actually branch to. But with branches, we have this funny business of take the number, the operand, multiply by 2, add another 2, and then add that to the address of the branch instruction. That tells you where you're going. There's good reasons why we add 2 here, and there's good reasons why we multiply by 2. I'm not going to go into those, but ask me about them if you're curious, or you can read about them in the data sheet. But they have to do with this recurring theme of trying to make life easy on the designers and on the hardware itself, and trying to make every bit count, every piece of silicon count. All right, so there's examples of this in the textbook. And here's a quick example of how we do this. But so when you play with branches, right? That's the procedure, and you can practice this on your own in the disassembler, right? Anytime that you look in here, this is guaranteed to be the correct bit pattern corresponding to an instruction. And so if I move this branch instruction somewhere else, let's put it down here and build that up. Well, now my branch is coded differently. It's D7F7. And D7F7, well, this number got smaller, right? Which means it's a different displacement that it's going to branch. If I move this branch instruction somewhere up here, so it comes actually before the label. Well, now it codes as a D001. And this 11-bit pattern is not going to be negative anymore, it's going to be positive. Because it's branching somewhere after its current location. In particular, it's branching to this next instruction right here. All right, so play around with those if you like. Let's see, quick question. Could we get some basic info on the midterm? See, it's due at the end of this month, which is coming fast. Yeah, your midterm is a week from Thursday. It's going to be similar to homework questions and stuff you've done in lab, basically. So make sure you know how to do all the homework questions that were assigned. And like I say, if there's a question that I did not grade, make sure that you're comfortable with what you did on it. Ask questions if you're not. A lot of these questions you can put them, you can use the disassembler or the other tools in MP Lab to actually check your answers. And I encourage you to do that while you're doing the homework and also, afterwards. So if you want to know about the access bit for question 10, right, you can write code that accesses different locations and see what that A bit gets set to. One of the nice things about this kind of stuff is it's really easy to check your answers, right, and confirm whether or not they're doing the right thing. You can check your code by running it through the simulator, right? We can, in some cases, we can go and we can actually change the values of memory locations. If you come up on the memory option, the memory menu, and so on. So I mean, you can use this tool for a lot more than we actually use it for in lecture and in lab. It can answer almost any question you have about your code or the coding of your instructions. But yeah, basically the homework sets and the labs are really good ideas of the kinds of questions that I'll throw at you on the exam. And next Thursday is the halfway point of the course, right? We're in week 3. It's an 8-week course, so next week's week 4, and then we're halfway done. So it's a really fast course in
way fast.
yeah, summer in particular. It's pretty quick. But, the good news is we've gone through most of a kernel of knowledge that you really need to do everything else in the course. The first half of the course that we're doing right now is really about kind of, the underlying architecture, the idea of program memory and locations in memory and file registers, and working with the coding, right? So MOVF, MOVWF, that kind of stuff. And then the second half of the course, roughly, is dealing more with the hardware. So we'll play around with these different hardware subsystems inside the PIC for doing timing, for responding to interrupts, for doing serial I/O, pulse width modulation, all kinds of things like that. But the tools we use for doing that are the stuff that we're learning right now, assembly language programming and using file registers and things like that. And so it kind of breaks into two nice chunks. All right, let me leave you with one more thing. When we're writing assembly language code for something like, if x equals y, we need to set the status register to tell us whether x is equal to y. Well, we can do that by subtracting. Take x, subtract y, and if the 0 bit is set, then we know x was equal to y. But what if we're not doing anything in particular? What if we're not, incrementing x or subtracting x from y or something, and we just want to know if x is equal to 0, go somewhere. Well, it's pretty easy to say branch of 0, ha ha. But how do we tell the system that we want this branch of 0 to be based on whether or not x is equal to 0? Because BZ is generally looking at the results of the previous operation, the last thing you did. And if we don't know what the last thing was that we did, right, we've got no reason to believe this is going to check to see whether x is equal to 0. So what could we do to update the z bit based on whether or not x is equal to 0? What kind of statement or statements could we write to make this meaningful so that this branches if x is equal to 0?
You could just move x into reg. Wouldn't that still evaluate to 0? If x is 0?
So let's look at this. Let's look at the MOVF instruction. So MOVF, and it updates 2 bits, 0 and negative. So yeah, we could MOVF into the W register, and that will update the 0 bit. Awesome. One thing to note here though, MOVF accepts a destination bit. Now usually when we say MOVF, we're trying to move a file register into the W register. But what would happen if we just said MOVF X and we didn't say comma W or comma 0? So what does this operation technically do? Where does it move X into?
It doesn't move it anywhere. It moves it into the file register it's already in.
Yeah, it basically copies X into itself. Which feels like a no-op. It feels like there's no reason to do that. Right? It's like taking a book off your bookshelf and then putting it right back in. You haven't accomplished anything, except that when you do a MOVF, the 0 bit gets updated. So you've taken the book off the shelf and you look to see if it was a certain book, and then you put it right back. And now you can do a conditional based on the result of that 0 bit. So this is the reason that MOVF allows a destination bit. Because if you want to know if a file register is equal to 0 or is negative, you can just move it into itself. And it doesn't change X, and it does not change the W register. And even though W is a temporary register, we've only got one of them. And so sometimes we want to keep a value in there for a few instructions, and this saves us from having to, overwrite the contents of W. So you'll see code just like this, just MOVF X with no destination bit. But then you can do a BZ or a BNZ afterwards. Yay, pointers. Alrighty, go ahead and send me one last attendance ping, and I will leave it at that. I will switch over to my office hours Zoom session and pop in there if you've got questions or things you want to go over on lab. Otherwise, keep finishing up lab 2, get started on homework 3, and bring questions on Thursday. I'll get homework 2 graded and back to you probably sometime tomorrow. And have a good afternoon, good day tomorrow, and I'll catch you next time. Thank you.
Have a great day.
Good afternoon.
Thanks, you too.
Thank you.